Okay, so now, okay, so we're going to talk about this, the signal equation today. So the signal equation is what is the signal that we record? What's the nature of it? So it's actually, the hard part to understand is, so last time we talked about the coils. So how do the coils work? And the plan was, if you have a coil, and then you've got two things going on. So you've got the, if you put some current around the coil, so if we put some current, there's a J, that's what we use for current. We put some J going around the coil, that's current. We get a B coming out like that. And then vice versa, if you put some changing B, it has to be changing. So if you put some changing B in the brain, it makes a current go in the coil. So that was the coil, but we didn't really talk in detail about, what is the signal in the case of having some changing B, like oscillating protons. So here's some oscillating protons going around this, going around this way. Here they're oscillating. What is the total signal that we get out of the coil? So that's what we want to do today. So total signal out of coil. So the bottom line is basically every data point. We'll just start every data point in MRI contains whole brain. So this is kind of hard to process, but every single data point that you record contains information from the entire brain, pretty much. So how does that work? So we'll start off with the popular signal equation. That's what I always say every year. Also, it just gives me a bit of a laugh to say this is a popular signal equation. It was very popular in high school. Popular person in high school. Okay, so what is the signal equation? And why does it contain information about every point in the brain? So we're going to start off with a capital phi. So when, again, like if you see that symbol, that's just a capital phi. So it's just like, that's not good. There must be something strange. So what is this? What is this? So that is this is called the magnetic flux. Flux capacitor. It's not a capacitor, just flux. Okay, so what is the magnetic flux? So flux, sort of means flow. So you might think that somehow implies movement, but it doesn't actually. So we'll get to movement, but there's no movement here. So if you turn a current on in a coil, the currents is flowing around in the coil. The result is a magnetic field, but that magnetic field isn't moving. So it was originally sort of described as lines. So if you put a magnet under some iron filings, you'll see that the iron filings sort of arranged in these lines. And that sort of gave the initial people fiddling around with this the idea that there was some kind of movement involved. But there's actually no movement involved in the magnetic field. You just turn a current on. The magnetic field just is static. It stays in the same place. And so what is the flux? So what the flux is, you can think of it as, so the flux is a scalar. It's not a vector. It's just a number. And what it is basically the magnetic total magnetic field perpendicular, in the case of a simple coil, perpendicular to the coil. So you can think of it as like, let's look at all the magnetic field vectors. So like here's the coil, and there's all these magnetic field vectors. So and they could be lots of different directions. And so here they are, coming through the coil, and coming through the coil. And so what the magnetic flux is let's get just the perpendicular component perpendicular to the coil, and just find that component. So this one's almost perpendicular, and then add it all up. So this perpendicular means perpendicular to the plane of the coil, and it's a scalar, so it's just a sum of all those lengths of the magnetic field vectors going through the coil perpendicular to the coil. So it's just kind of a measure of like how much magnetic field is there perpendicular to the coil. That's the magnetic flux. And so how do we calculate that for an actual object in the coil? So that's what this first equation is. So the first equation is we integrate, which just means sum. So we sum across the object the following thing. And so the following thing is we have a B and an M, but now we're doing a dot product. So that's why we had to do the dot product at the beginning. So this is the dot product, but we've got two vectors there. So let me just write it out first, and we'll. So here's the magnetic field, and this one might be changing in time. And this dr means, for each little volume. So what's the r vector first? So the r vector is basically just, x, y, z. It's basically a voxel. So it's just one x, y, z point. So we could write this out as b vector x comma y comma z comma, but since we're going to be like good mathematicians, we'll shrink it down to just one letter, r, so we don't have too many letters. So that's what the r vector is. The r vector just means, here's our coordinate system. The r vector is just a particular point in 3D. So it's just a particular point in 3D. So here's the x, y, z coordinates of that point in 3D. So that's the r vector. And for the B field, and that's related to the coil geometry. So what is this? This is the magnetic field detected or generated by a coil. For each point. So the magnetic field doesn't have to be all the same, different. And in fact, the magnetic field, if you turn some current on in this coil, the magnetic field will curl around the coil. It will curl around the wire of the coil. So it can be different at different points in the brain, but this is at each point, just put in brain. So each point in brain. So that's a property of the coil. It depends on what the shape of the coil is. So that's the first B, and now we're crossing it with, we're dotting it with M. So this is, dot product. And remember what the dot product was, if the vectors are similar, it's big. If they're perpendicular, it's 0. So the dot product with this. Now what is this thing? So this thing is basically the local magnetization. So it's the local magnetization, of object brain. So what this means is if you go into the object, so at each point in the object, so this means, at each point in the object, there's going to be a certain magnetization, which is, whatever the, at a particular point in time, what is the total magnetization in that little voxel, average magnetization in that voxel? It's pointing in some direction. It could be any direction. We'll see in practice we can only pick up the xy component of the direction. We can't pick up the z component of the local magnetization. So we can only pick up the xy. But if you dove down into the brain, you'd see that it would actually be pointed, there'd be a z component also. But we can't pick that up. So it's the local magnetization, and then basically just, across all brain. This is for each voxel. So this just means sum across brain. So what does that equation say? So that equation says, first there's two magnetic field directions. One is what magnetic field direction will you get if you turn on some current in the coil? And then there's another magnetic field direction, which is what magnetic field direction is currently present at that point in the brain. And then we do the dot product, which means how similar are they to each other. And if they're similar, we get that voxel has a big signal, and then we add up all the voxels. And the end result is the flux through the coil. Okay, so flux isn't any good. We need to actually know what the voltage in the coil, we need to know what the actual signal in the coil is. And so to get that, we need to take the derivative of this guy. So the voltage at a particular time in the coil is going to be equal to the negative of the partial derivative of this guy. So what is the partial derivative? The partial derivative means is the change in the flux just with respect to time. So we'll just ignore the space part. So we just want to know how is the flux. It might be different in different parts of space, but ignore that. All we want to know is how does it change in time across all those different places. So that's what this partial, so this is partial. I mean, only pay attention to time. Only attend time. Okay, so what is that? So this thing is called, it's called the Faraday law of induction of currents. So if you change the flux, if you look at the negative of the change in the flux, that tells you how much voltage you get. So it's basically just directly proportional to the rate of change of the flux. So if you change the flux, which means change the magnetic field coming perpendicular to the coil very rapidly, you get a big voltage. If you change it slowly, you get a small voltage. And so then, but that means we have to take the derivative of something. So what we need is the partial derivative, just paying attention to changes in time of this thing. So here's that. I'll just write it out again. So here's the dot product between the magnetic field that the local coil generates and whatever the current magnetic field is at that for each point in the brain. Okay, so now we got to take the derivative of this guy. So how are we going to do that? We don't know what this guy is, right? This could be this could be like, who knows what we have in the sample. Maybe we turned the gradient on, maybe it messed up we turned an RF on, who knows? It's just like some completely unknown function. So what we need to do to get our derivative is we have to come up with some function here. And so we'll just make one up. We'll make up a simple one and solve for a simple one. So you often do this in math. You got sort of a complicated general thing here that's underspecified. It just says it's the derivative of whatever this is, and I have no idea what that is. Well, it's hard to take derivatives of things, especially sort of random looking things. And so let's just make one up. So we're going to make a whole bunch of assumptions to make this easier to solve, and I'll write them all down here. So the first assumption is we just ignore z. So z component. So why are we doing that? I didn't really explain it before. I would just say a little bit more about that. So we're recording, it's called the RF coil, which means radio frequency coil. So what is radio frequency? Well, radio frequency are like the frequency of a radio. So like, FM radio is about 100 megahertz, 93.1, that's 100 megahertz, 93 megahertz. But it's a relatively high frequency. So it turns out that if you just turn on a current and generate a magnetic field, you don't get any radio waves. You get a magnetic field, but it falls off quite quickly. So what are sort of radio frequency, what's going on there? Well, this was figured out in the late 19th century, that if you very rapidly wiggle the magnetic field or the electric field, what happens is the magnetic field and electric field become coupled to each other. And this only happens at very high frequencies, like, you need like a million cycles per second. And when that occurs, magnetic fields and electric fields can propagate off across space. Now, normally, that's what the Maxwell equations describe. They describe how these electric field plus magnetic field, not electric current, electric field plus magnetic field get coupled to each other and cause this disturbance to propagate across space, or propagate a very long distance across space. So that's radio frequency. When they say RF, your cell phone, when you're thinking of those kinds of things, that's radio frequencies. And so that's the kind of thing that we're recording. We're actually recording these radio waves that are electromagnetic, electric field plus magnetic field, that are coming off these precessing protons. So why is that important? Well, we would never pick up anything from one of these precessing protons if we'd have to get really close to it in order to actually pick up the static field of it, if you could ever get it to be static. But instead, we're picking up, that thing is sort of generating the radio waves which propagate out of the brain into the coil. So that's actually what we're recording. We're recording these coupled electric and magnetic fields, waves that are coming out. Now, it turns out, so at very low frequencies, you do get some waves, but they're really weak, extremely weak. And it's possible if you put a huge amount of power in, you can actually make a strong, very low frequency radio wave. That's actually possible. And they've even tried to use this to sort of figure out where submarines are underwater by hooking a whole power plant up to an antenna and generating just putting a huge amount of current, so you could actually generate a very low frequency radio wave. So it's not like it doesn't happen at low frequencies. It happens, but it's so small you can just throw it out. And the Z component is like that. And so why is the Z component like that? Well, what happens is, if you're watching these precessing protons, we drew it like this. So they precess around, and then you get T2 decay, and then they start, going up to the Z-axis. But I didn't draw the right number of cycles. So there's like about 1 billion cycles in here. I only drew like 25. Okay, so this precession action is very rapid, generates nice radio waves. The growth along the z-axis generates very, very infinitesimal, completely unrecordable waves. And so basically, you just throw away the z component. So the only signal that you get out of the brain is basically just the xy component. These radio waves generated by the xy component of the oscillation of the rotation of the protons. So that's the first thing. Okay, so now let's just substitute in a typical signal, local signal. Okay, so what is that signal? And so here's the signal we're going to use. We're going to use the xy component. So that's just the x. So now we've gotten rid of the z, so we just have the xy component of this magnetic field vector at a particular point in time. And we're going to use that for this number here. And so this function here. And so what is that? So it's going to be equal to however much magnetic field we started with, xy magnetic field we started with. And that's going to decay. Remember, it's going to decay a little bit because we have the Bloch equation. It's going to decay a little bit. Local signal lab frame. It's going to decay a little bit. It'll start, at time t equals 0. That's e to the 0 is 1. So there'll be no decay at the beginning. You'll be multiplying by 1, but over time it'll fall off. But then we're also going to multiply by this guy, which is the actual oscillations. E to the I omega t. Okay, so that's what we're going to substitute in. So this guy is complex. This guy is just a scalar, just an amount. This guy is also a scalar. And then this guy is complex. That's what makes this guy complex. This makes this guy have imaginary components. So this guy's complex, amplitude equals 1. Amplitude equals 1. So remember, that just stands for, that whole mess there just stands for a vector of length 1 at some angle around the origin. So that's still kind of a mess. So we still want to get rid of some more stuff. And so what's the next thing we'll do? Let's ignore decay. Just assume t equals 0. So if t equals 0, then we can just cross out this guy. So we can deal with decay later. We'll it just complexifies thing. Okay, now so now we could sort of take just the derivative of this guy. So before we simplify it even more, let's just take the derivative of this guy. So what does that guy consist of? So we could take. So we need to take the derivative of this guy. So we could just take this derivative guy. This guy is not dependent on time, so we can just ignore that. So we can just put this derivative right inside here next to this m guy and take the derivative of him. So there's two ways of doing it. So one way of doing it, we could think of it in terms of sines and cosines, because this thing kind of stands for sine and cosine. And so let's just sort of quickly go through that. So what's the derivative of cosine? So here's cosine. That guy's cos. So that's cos of, say just 0 to 360 here. That's cosine, 0 to 2 pi. So what's the derivative of that? Well, it turns out the derivative of that is just the minus sine. So this would be the sine. And so if we take the minus sign, that turns out to be the derivative. So the derivative of cos is just minus sine. That's kind of cool. So what that means is, what's the derivative? It's just the slope. So the slope of the cosine is 0 right here. So that's 0. And then it starts going down here, and here's where it's the biggest. And that's, if I had drawn it right, that would be the biggest value of the negative cosine. It's the biggest negative value because it's the negative cosine. And then when you get to this point we're back at 0. And then at this point, it should be the biggest again, slightly warped. Here, there we go. So derivative of cosine equals minus sine. And derivative of sine just equals cosine. So that's kind of handy. So our derivative is just going to be, sines and cosines. It was sines and cosines before. But remember, this is, if this is, say, like 1 second of signal, we're going to have 123 million cycles in there. So it won't look like that for, if this is 1 second, it's just going to look like, that's the derivative is going to be very steep. So we're going to have to multiply the derivative, times whatever the frequency is. So the derivative is going to be like 123 million times the cosine of something. It's going to be a big number. So that would be how to do the derivative, as cosines and sines. But over time, you just do the derivative directly on that guy. And so how do you do the derivative directly on that guy? Well, so the derivative of, with respect to time of this guy, e to the minus I omega t. So we take the derivative of the exponent and multiply it by the thing. And so what is that equal to? Well, it's just the derivative of this guy. So time is to the power 1 here, and so we reduce that power 1. So we get 0, which is equivalent to 1. So that comes out to, leave out the negative for now, just make it simpler. And so that comes out to an I times omega times e to the I omega t. So that's the derivative. So now there's a couple things like, okay, so now we can see that so remember this guy is just amplitude 1 for a particular time, and so this one keeps cycling around and around and around every time as you get higher and higher in higher and higher angles. So these angles get really big here, right? So after 1 second, that's an angle. After 1 second, the angle here is going to be 123 million degrees. So that's going to be a very high angle, but the end result will just be a vector, pointing somewhere around, just wrapping around on itself over and over again. But now we've got this guy out here, and that makes sense again because we had to sort of consider there were 123 million cycles in 1 second, and so the derivative is going to be very big, multiplied by this very big number. But then you've got the I out there, and when I first saw this, I go like, what's it doing out there? I had it safely inside here in the exponent, so I could just sort of turn it back into something like that. But now we've got an I outside. So what does that mean? Well, that just means rotate by 90 degrees. So if you remember the multiplication rules for complex numbers, you multiply the amplitudes, and the amplitude of this guy is just 1. Because, what is that? What is an I? An I is just like that. It's just a radius 1 upward vector. That's what an I means. Because there's no real part of that. It's just a pure imaginary thing of amplitude 1. So we multiply by 1. Well, that doesn't do anything. And then we add the angles. And what is the angle of that guy? 90 degrees. So when you stick an I outside like that, all it means is just rotate this complex number by 90 degrees. And, it's kind of, you've got sine turning into cosine. It sort of makes sense here. You sort of moved over 90 degrees. Okay, but we're going to simplify that. Okay, so we don't want that. That's too complicated. So now we have to assume that we've done phase-sensitive detection. So I didn't explain what that was yet. I'm explaining it on Monday. So assume phase-sensitive detection. And what is that? That is, don't tell me this 123 megahertz business over here. All I want to know is, what is the frequency difference between our center frequency? So like a spectroscopist would, like what is the shift? What is the shift in frequency? I just want the delta frequency. I don't want the whole frequency. So that's what we want to do. We want to just assume we did phase-sensitive detection, and so we're just getting these frequency differences. And we'll explain exactly how you can get those frequency differences, even from one coil. So that's this important point here, that phase-sensitive detection basically makes a two-dimensional signal. Even if you just give one voltage coming, you get one voltage stream coming out of a single coil, you run it through phase-sensitive detection, you get two signals. It's totally critical. Can't understand what's going on without those two signals. So that's what phase-sensitive detection does. You could also have like two coils, like say like a sideways coil in the bore and a top coil in the bore, and those would give you two signals. But it doesn't. You don't even need that. Just one coil. After you run it through phase-sensitive detection, you get two numbers. Okay, so let me just write that out. So our signal now we've got sort of a complex signal, is after we've taken the derivative is going to be equal to the sum of just the xy component of our magnetic field times this thing now. So what we've done is the phase-sensitive detection, we've taken omega and then just looked at what is our offset frequency, the delta omega, not the actual 123 megahertz. We just want to know like 200 hertz. We're 200 hertz off of our center frequency, shifted off of our center frequency. So here's that equation that mxy at a particular point in the brain, and at time 0 because we got rid of the decay, and then finally we're multiplied by just this last thing there, and that last thing was E. We'll put a minus in there. So that offset frequency, and that offset frequency, however, is dependent on where you are in the brain. So there's a different offset frequency for each point in the brain times the current time summed across the whole. Okay, so we're almost to the popular signal equation. So now let's throw this guy out. Let's just assume we have like a really uniform coil. Ignore for uniform. And then what about this I business? We had that I. That would have been over here. So, ignore phase offset. There should be an I in there, but we'll just get rid of it because it just messes things up. It's just rotate by 90 degrees, so let's just say we'll subtract off 90 degrees. We don't care about that. So finally, we get to the popular signal equation. So let's write this down. So this is our final answer. So our complex valued signal, which we didn't describe how we got it, but it's got two components to it from the phase sensitive detection. So this guy has a real part and an imaginary part, is equal to the sum across the entire object of the xy component of the magnetization, xy, at a particular point in space, and at time t equals 0, because we're ignoring the decay, and then finally times e to the minus I delta omega, the change in frequency at a particular point in space, that's the r, times time, summed across the whole object. So this is our popular signal equation. Now we just have to sort of look at this and sort of figure out what this means. So this is our bottom line. For our very simple case, we're just assuming that at each point in space, we've got something like this. We just have a simple oscillation at each point in space, and we know that the protons do this simple oscillation. We don't know what the frequency is. It could be a different offset at each point in space. We've gotten rid of any unusual aspects of the coil. We're just assuming the coil is all completely uniform. We've thrown that all out. We've gotten rid of the decay. And so stripped down to its absolute minimum, this is the signal that comes out of the MRI machine. It's a complex valued signal at each point in time. And so what is it? So what does this equation actually say? So just, geometrically, what's going on here? So say we just, say we look down at the magnet from the top. So we're looking at the magnet top view. Let me make it a little bigger, sorry. So what are we really saying? So here's a nice big magnet. So what does this equation say? So for an instant in time, it's important. There's an instant in time, just like a snapshot, very small chunk of time. What does the equation say? It just says, look across the entire sample and do a complex sum. So this is complex addition. Complex add. So complex add across so that means vector sum. So translated, that means vector sum. (2D) vector sum, because we're only doing xy, of what? So how strong the magnetization is at a point, so that's a scalar. So that's just how strong it is at this point in the brain. And then we're multiplying by amplitude 1. So remember that's just some amplitude 1 vector around the circle, around the xy plane. So let's just draw that out in our magnet here. So here's our magnet. So at this point, the magnetization vector is there. At this point, it's a smaller one there. This point, it's a big one. Here's a smaller one, big one, smaller one, big one. So there's our happy person in there. Okay, so it's filled with magnetization vectors. They're pointing in all different directions in the xy plane. We're looking down, top view. And all we do is just do a complex add. Complex add is just a vector sum. So we just add all those guys up. And what do we end up with? One vector. So here's the coordinate system. Say that's radius 1. We just end up with one vector. And it's got a real part, and an imaginary part. So this is one data point. So that's all. So every single data point in MRI looks like this. It's just a vector sum of the local XY magnetization across the entire sample. And all images are made out of that. You cannot not record the entire brain. Even if you have a local coil someplace, it doesn't matter. It's seeing the whole brain. Yes, some parts of the brain are a little dimmer. It doesn't matter. It's seeing the whole brain. It's actually seeing the whole body. So this is a single data point. This is what it actually looks like. So every single data point is always a vector sum of this local magnetization summed up across the entire sample. There's no space in it at all, really. So you somehow have to extract all these tiny little voxels out of this kind of stuff. That's exactly what the Fourier transform likes to do. So we'll sort of go in that in a lot of detail. But basically this is, so one data point at instant in time. So at a later point in time, the data is going to go, the data is going to be something else. So here's, so here's time t1, time t2. So we'll get a different set of real and imaginary signals for some other point in time. So, okay, so the popular signal equation. So this is, it's critical to understand this. It's really, literally just the tip to tail vector sum of the XY component of the magnetization across the entire sample, summed across the entire sample. And somehow out of that, we can actually make, 16 million voxels. 16 million 1x1 voxels. Okay. So I think this is quite confusing, but let's end the recording, David, and we'll take some questions.